All right, welcome back, everyone. Okay, so I have a website now. You can all log on to, or just go to my website. That's faculty.washington.edu/sbrunton/ME564. And you'll have a list. Sorry, the resolution is completely bombed right now. You have video lectures, so you can go and actually watch these recorded lectures if you want. You can download them in HD. They're about 1 gig each. The homeworks will be posted. There's no homeworks actually posted right now. I think I'll probably post the first homework sometime over the weekend or on Monday. It'll be due on next Friday, and it'll cover material through the Wednesday lecture of next week. Okay? This should be mostly introductory stuff, so hopefully it's not going to be too intense, and it's not going to be like super long either. Anything else? Yeah, so I actually post all of the lecture notes and syllabus online. So this is going to keep developing. Every time I give a lecture, I'm just going to add a line here discussing what I do. There's a link to the PDF notes that I've scanned in and any MATLAB codes that I generate. So for example, right now you can actually download the notes for today. I've already downloaded them. And these are all of my notes for today. Okay? Okay, I think that's it for the board, for the computer. Any questions about the class now that everyone's had a little bit of a chance to think about things? No? Okay, so today I'm going to do a few things. This is going to be a pretty important lecture because this is really where a lot of the review for the class will take place. And in the next lectures, we're just going to keep building kind of faster and faster until we saturate. Okay? So I'm going to give you a little overview of the topics I'm going to discuss today. Now, some of this is definitely going to be review for a lot of you, but I'm hoping that pretty quickly we'll get into things that most of you hadn't seen before. Okay? So first, we're going to review some calculus. Okay, so this will include the derivative, the power law, and the chain rule. Okay, so this will be pretty quick. I'm going to start talking about the simplest ODE. So the simplest ODE, which is just x dot equals lambda x. So we're going to think about where this comes up in physical systems, engineering systems. We're going to look at a few different ways of solving this. I can think of 3 off the top of my head. We'll do 2 of them today. We're going to talk a little bit more about what is the exponential e. And this might sound really, really simple, but this is extremely important. Okay, so all of these concepts are going to be extremely familiar by the end of this class. We're going to be using these every day as if we're adding numbers. Okay, and then the 4th topic is solving this equation, x dot equals lambda x, using Taylor series. Okay? And there's a good chance that number 4 will actually be something we do on Monday. Okay? So this is probably for the next lecture. Okay, so that's just what I want you to kind of have in the back of your mind. This is the progression. We're going to solve simple ODEs starting with x dot equals lambda x. We're going to think about lots of ways to do this. Pretty quickly, I want to get into very general ways of solving this where we actually derive the solution instead of just use tricks from calculus. And then we're just going to build it up to systems and nonlinear systems quickly. So any questions about this? Nope. Okay, and feel free to interrupt at any time. That's totally fine with me. All right, good. So everyone's taking calculus. Some of us have taken it multiple times or in different contexts. And so you've all seen the derivative and the integral. And I'm just going to kind of briefly go over, just to brush up. I know some of you, it's been a while. And so we're just going to kind of all get on the same page of what the derivative means physically and geometrically and mathematically. Okay? Okay, good. So what does the derivative mean? Anyone?
Rate of change of a function.
Okay, the rate of change of a function. Perfect. Rate of change of a function with respect to what? Yeah, with respect to x. I probably shouldn't post my notes while I'm giving the lecture. Okay, so this has a super, super simple geometric interpretation. Okay, and this should be something really familiar to all of us. There's a ton of calculus I've forgotten. I'm going to be completely honest, right? There's just a tremendous amount of calculus that I learned and don't remember. But you can almost derive everything if you know a few first principles. Okay, so when I teach my undergrads, I teach them more formulas. I want you to know first principles. 10 years from now, 20 years from now, it doesn't matter what formulas you remember. It matters that you can derive things from first principles. Okay. So we have some function f of x. We care about looking at the derivative at some point x. And we think that the derivative means the rate of change of f with respect to x. And that means the slope of the tangent line at that point x. Okay, so we can do a pretty good job of approximating this derivative, df dx. This is going to approximately equal f at x plus delta x. Okay, so this is x plus some little delta x away. Delta x is small. Minus f of x divided by delta x. That's just a formula for how much does the f variable change over dx. Okay? df dx is approximately this. And if we make delta x smaller and smaller and smaller, so we bring this right point closer and closer and closer, we converge to the true derivative of that function at x. Okay, so usually we put this limit as delta x goes to 0, and now this isn't approximately equal, it's exactly equal. Okay, that's the derivative. Okay, super important stuff. It's blew everyone's mind when Newton and Leibniz came out with it. It's changed the world ever since. Okay, that's the derivative. We're going to use this a lot. We're going to take it for granted a lot, but I don't want you to take it for granted. So a lot of times we're going to drop this limit, and we're just going to assume that delta x is small. Okay, so in calculus, we always take this limit as delta x goes to 0, and we do mathematical things. We're going to do a lot of things in a computer, and we're going to think that the derivative is approximately equal to this difference divided by dx for a small but finite dx. Okay? Okay, good. So now we're just going to do this on a simple example of a function x to the n, and we're going to derive the power law. So this should be one of the straightforward things we can do in calculus. Okay, so we're going to try f of x equals x to the n, and this is called the power law. Okay, so we all know what the derivative of x to the n is. It's df dx equals n times x to the n minus 1. But we can derive it pretty simply from this formula over here. Okay, so I'm going to say df dx is approximately equal to 1 over delta x times f at x plus delta x. So that's x plus delta x to the n minus f of x, which is just x to the n. Okay? This is f of x plus delta x. Okay, so how many of you remember how to take x plus delta x to the nth power? There's a few ways to do it, lots of ways. Anybody? There was this guy, his name started with a P. Pascal, right? There's a programming language named after him. So Pascal's triangle kind of gives you a quick and dirty formula for computing this. You could also use the binomial expansion. And you get, so 1 over delta x times, let's try not to mess this up, x to the n. Okay, that's the first term. Then the second term, you're going to do all this multiplication and collect all of the x to the n minus 1 terms. And you're going to have n of them times the delta x. Then you're going to have an n times n minus 1 divided by 2 times x to the n minus 2 delta x squared plus dot, dot, dot. A bunch more terms, right? N plus 1 of them. And then we still have this term left over, minus x to the n. Okay, good. So this is just using Pascal's triangle or binomial expansion. My x to the n's cancel. And I'm left with 1 over delta x times all of this stuff in the middle. So that's n x n minus 1 times delta x plus n times n minus 1 over 2 x to the n minus 2 delta x squared plus, and I don't want to write all this other stuff down, so I'm going to say everything else is on the order of delta x cubed. So delta x cubed, delta x to the 4th, to the 5th, and so on. So it's on the order of delta x cubed and higher. Okay? And now what I'm finally going to do is I'm actually going to divide out my delta x now and take the limit as delta x goes to 0. So we have n x to the n minus 1 plus a bunch of stuff that's ordered delta x. And this goes to 0 when delta x goes to 0. Okay, so starting with a very simple physical definition of the derivative, it's the rate of change of f with respect to x. It's the slope of this tangent line. Using this formula and then essentially plugging in any function we like, we can derive the derivative. Okay, this should be review for most of you. If it's not, you should do this on a few functions and get a feel for this, okay? Okay, any questions about the derivative or the power law? Yeah?
This is 0, delta x cubed.
I'm sorry? Yeah, so I had these order delta x cubed terms. I also had order delta x squared. So when I divide by delta x, I have an delta x plus delta x squared plus delta x cubed, and I lump them all into this term. Yeah, so sorry, I'm being a little fast and loose with this notation. This just means I have this term, which is not multiplied by delta x, and then everything else is multiplied by at least 1 delta x, maybe more. Okay, so those all get limited to 0. Yeah, good question. Okay, so another super important kind of calculus rule that you can derive is called the chain rule. This is the most important in my opinion. Okay, and that just says that the derivative with respect to x of a function f of another function g of a variable x is equal to f prime of g of x times g prime of x, and prime just means derivative, df dx. Okay, prime means derivative. So this is really, really important, the chain rule. This is how we solve complicated calculus problems, right? You could do like sine of x cubed, and you could find the derivative using the chain rule. Okay, so again, if this is something that you've seen before but you don't really feel super comfortable with, just try a couple of functions like that, get the hang of it. You can always check them on Wolfram Alpha to make sure you're doing it correctly. Okay? Okay, good. Now let's get serious here. Now we're going to start talking about differential equations. So calculus is one of the fundamental languages that we use to communicate what we observe. Things change in time. Things change with respect to variables. And now we're going to figure out how to use that to solve, essentially, to do problem solving to model the real world. Okay, so differential equations is probably, along with probability, the most useful technique for modeling the real world we have. Okay. So I always like to start with a really, really simple example to motivate ordinary differential equations. We're going to come up with a bunch that are relevant for things that we do. But let's say that we start with a population of bunnies. Okay, so x is the size of a population of bunnies. Okay, and what do we know that bunnies like to do? Procreate, right? Bunnies procreate. And so what we have is the size of the population, x, changes at a rate that's proportional to the size of the population. The more bunnies, the more procreation, the more baby bunnies. Okay? And so the population changes in time. This is dx with respect to time. We're going to call that x dot. So dot is specially used for time derivatives. Dx dt equals x dot. This is going to be proportional to the size of the population. Okay, this is our simplest differential equation. X dot equals lambda x. Okay? Now, there are a lot of ways to solve this. The basic question we're going to ask is, what is the size of the population, x, as a function of time? Okay? How does this population change in 2 years, 3 years, 4 years, 5.5 years? Anytime you specify, I want to be able to tell you how many bunnies there are if I know how fast they procreate. Okay? Okay, so how do I solve this problem? What are some ways to do this?
Separate the variables and integrate.
Okay, I can separate the variables and integrate. That's a good idea. Let's try that. Okay. Okay, so separating the variables and integrating basically means keep all of the x's and dx's on one side, move all of the t's and dt's to the other side, and then integrate both sides, right? Okay, so we have dx dt equals lambda x. And so that basically means that I can divide both sides by x and have dx over x equals lambda dt. Right? And if I integrate both sides of this with respect to x on the left and with respect to t on the right, then what's the integral of dx over x? Natural log of x, right? So ln of x of time. X is a variable of time. Remember here we're only integrating with respect to x. And that equals, what's the integral of number times dt? Just that number times t, right? Lambda t and And I get a constant, right? I always have an integration constant, because if I took the derivative of this, any number here is going to go to 0. Okay, so how do I solve for x? E to the both sides. Okay, so x of t equals e to the lambda t plus a constant. And the nice thing about exponentials is that e to the a plus b equals e to the a times e to the b. So e to the constant is just another constant, just another number. Right? This equals e to the lambda t times k, another constant. Okay, we're getting there. So our function, our population x as a function of time looks like this exponential function, e to the lambda t, times some number k. So what's k? How would I figure out what k is? Well, okay, so what does initial condition mean? It means I look at what my function was at time 0. Okay? So if I plug in x at time 0, then that's, x at 0 is e to the 0 k. E to the 0 is 1. So k is my initial condition. It's the size of my population at time 0. Like right now, I have 50 bunnies. In 5 years, I'm going to have e to the lambda 5 times 50 bunnies. Okay? Okay, so the full solution is x of t equals e to the lambda t times my population at time 0. Okay, really important equation. Simple, but important. Okay, any questions about exponentials, the first order linear differential equation? No? Okay. How many of you remember what this number e means, what it is? How many of you don't quite remember exactly what e means? I'm guessing some of you, because before I gave this lecture a few days ago, I was thinking to myself, what exactly is e really? Okay, so I want to think about what is e, the number e, really. Okay, so how do we usually learn about what e is? Like in school, when you learned about e, what did your teachers tell you? Well, they told us about bunnies procreating. They told us about compound interest. So compound interest, I think, is the absolute simplest way to think about this because we get a limit out of it. So let's do that, okay? So we're going to do a simple kind of problem. This is the way I like to do things, is think about word problems. Okay, we're problem solvers now. Okay, so I'm going to take out a loan L to buy a car. Okay, I need a new car. My car's a piece of shit. I need a new car. I'm going to take out a loan, and I'm going to buy a car. But I have an interest rate R, and so maybe every year I'm going to have to pay R% on the loan extra. Okay, something like that. Okay, so there's a few ways to do this. If your bank is nice, they'll compound at the end of every year. So compound yearly, which would mean that, so let's say that my loan amount is a variable x, okay? So x at time 0 is L, okay? x0 is my loan amount. Okay, so if my bank is nice and they compound yearly, then x of 1 is going to equal 1 plus r times L, or times x naught. Okay, what are some nasty tricks my bank can play on me? Well, they could change my rate. Let's say I have a fixed rate loan. They could compound monthly. Okay, so what that means is that x at year 1, I took Okay, in the first month, I took my loan amount times 1 plus r over 12. Okay, so now I took my yearly interest rate, I divided it by 12, and that's how much my loan increased in the first month. But now in the second month, I'm paying that rate on my original loan amount plus the interest I've accrued in the first month. Okay, so I do that over 12 months, and I get this nasty expression 1 plus r over 12 to the 12th power. Okay, and this is a little bit bigger than r. It's not much, but it's a little bit bigger than r. You can use the same formula we used for the power law. Okay, and you can essentially take the limit as your little delta t goes to 0, and you can compound continuously. So my bank is compounding my interest right now, and now, and now, and I'm paying interest on the interest that I accrued in the last second, in this second. Okay, and we find that x at time 1 is equal to the limit as the number of divisions goes to infinity of 1 plus r over n to the n times x 0. Okay? And this is the definition, or one of the definitions, of e to the r. Okay? E to the r is this limit if you just compounded interest. So this is like my bunny population. It's proportional. The amount of increase to the bunny population is being compounded continuously. And if you take that limit, you get e to the r. Okay, if I pull up my computer, let's see if I can do this and actually get the computer to show. Okay, what was e to the 0? 1, right? Let's see if this works. Okay. Right. So e to the 0 was 1. Let's say that my interest rate is 5%. Okay? So after 1 year, EXP of 5%, or 0.05, what do we expect it to be about? Well, it's, e to the something small should be close to 1. Now, it should be about 1 plus 0.05, right? Because if I compounded yearly, it would just be 1 plus 5%. But I'm compounding continuously, so it should be a little bit more than 5%. And I get 1.0513. Okay, so if I have a 5% interest rate and I compound it continuously, I'm paying about, 0.13 extra percent, which is a lot of money to banks, right? Okay, that's what E means to me. It's you take this limit and you compound continuously. So it's the difference between discrete compounding events and continuous compounding events. Okay. So the bunny example is actually a little bit wrong, right? Do bunnies really compound continuously? No, right? Maybe they compound once a year or twice a year or 3 times a year. So I just want to think about, I want you to be thinking in the back of your head, if I ever say something that doesn't sound right, think about what the assumptions were that went into this, okay? Okay, so let's think about another example. Actually, why don't we just write down the interest rate problem kind of formally, right? So what we're saying is that the interest increases continuously at a rate r that's proportional to the amount that I owe. So my interest rate changes continuously in time at a rate r that is proportional to my amount of loan at time t, right? First order, simple, linear ODE for the interest rate. Okay, and we know how to solve this. Good. Now, if we wanted to, we could say that this is the change in my interest rate over a fixed amount of time, like 1 month, is equal to R times my instantaneous loan rate times some delta t. So this would be what I wanted. If I wanted to model the bunny problem, let's say bunnies procreate twice a year. Okay, then I might write the system like this. Every 2 times a year, my bunny population discretely increases at an amount equal to the rate of increase times that population times that dt. Okay? And this is going to be the basis for numerically solving these ODEs. We're just going to pick small dt's and actually step these things forward. So soon we're going to do that. Okay, good. What are some other examples of simple linear first-order equations in engineering? Any of you live around Hanford, Washington? Yeah? So what's the big problem in Hanford? Waste, right? Radioactive groundwater. So why is this such a big problem? Because it heads towards the river. I think the big problem is that our favorite radioactive material lasts for a ridiculously long time. Okay, so plutonium has an incredibly long shelf life. Okay, so that's going to be another example. Radioactive decay. Radioactive decay. So radioactive decay, we can say that the amount of radioactive isotopes is decaying. So there's some minus, it's decreasing at a rate that's proportional to the size instantaneously of that pool of radioactive waste. Okay, so the number of isotopes is decreasing at a rate proportional to the number of isotopes. There's, breaking occasionally. And so we know the solution to this. This is, x of t equals e to the minus lambda t times x naught. Okay, so if I have 1 pound of plutonium, then at some time t in the future, I'll have e to the minus lambda t pounds of plutonium left over. Okay? Plutonium is nasty stuff. You don't need a pound. A pound's a lot of plutonium. Okay, so what we're going to do is kind of turn this on its head. So we know what the solution is. And let's say that we want to solve for lambda. Okay, so I know what the half-life of plutonium is. Okay, so plutonium has a half-life of about 80 million years. That's big, okay? So 80 million years later, I'll have a half a pound of plutonium for my 1 pound that I started with. And using this basic number, everybody likes to talk about half-lives, but I like thinking about what's my decay constant, what's my proportional rate of decay. And we can use that to solve for lambda really, really simply. Okay? So we know that at 80 million years in the future, when t equals 8 times 10 to the 7, I will have half of x naught left over. Okay? So x naught over 2 is going to equal to e to the minus lambda times 8 times 10 to the 7 times x naught. Pretty simple, right? This is, not even calculus. Okay, we're going to cancel our x naughts and we're going to solve for lambda. So what does lambda equal? It equals ln of 1/2, right? Then I multiply both sides by negative, and I divide by 8 times 10 to the 7. So minus divided by 8 times 10 to the 7th. Okay, that's what lambda equals. This is my decay rate, my proportionality constant. We could plug it into MATLAB. You'd find that it's a really, 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 really small number. Okay? So you can find out what lambda is for your favorite radioactive isotopes if you like. Any other favorite radioactive isotopes? Any Russian assassins in the audience? So if I wanted to kill someone with a radioactive isotope, and I didn't want there to be evidence, what would I do? I would use something with a really short half-life. So a really short half-life, what does that mean for lambda? Big and negative, right? A big negative number. So who knows what a really good radioactive element is for killing Russian dissidents? Polonium, right? Anyone know what the number is? I don't either. Okay, what is it?
I'm just venturing, I guess.
239, maybe.
Sounds nice.
Question mark. Okay, so polonium has a half-life of 138 days. Okay? Okay, 138 days is a little bit over a third of a year. Let's just call it 0.35 years. Okay, so you see that there's this huge difference in half-life. 8 orders of magnitude difference in the half-life of this thing. And we can solve for the lambda constant in exactly the same way. So lambda equals minus ln of a half, which is just a small, a positive number. And now instead of dividing by a huge number, we're dividing by a small number, 0.35. Okay, so this is now a much larger number, and there's always a negative sign out front. So this decays much, much more quickly. Lambda is much, much larger. Okay?
Polonium is 84.
84? Okay, way smaller. 84. Okay, good. Any questions about kind of this model for radioactive decay? This is actually way, 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 way more accurate than the bunny model, right? Bunnies don't really grow exponentially, but this almost exactly does decay exponentially, right? Like we're really relying on the statistics of very large numbers. If I have a pound of plutonium, that's some astronomical amount. Actually, it's not astronomical, it's just a pound, but it's a pound of plutonium. It's, lots and lots of atoms. And they all act quantum mechanically. And so, this really is almost exactly a true model of the system. So that's also something I want you to think of is how good are our mathematical representations? Where could error crop in? What does that mean when we have error? Okay, so I have one more example, and then I'll give you kind of a hint of what's coming next week. And then we'll go for the weekend. All right, so the last example is thermal runaway. Okay, so how many of you have suffered from thermal runaway before? I know I have. One time in college, my computer caught fire because of thermal runaway. So who knows what thermal runaway is exactly? So there's this unfortunate little quirk in some silicon-based electronics that when they get hotter, they become more resistive. And therefore, they get hotter and hotter and hotter and hotter. Okay, and they get hotter at a rate that's proportional to how hot they are. Okay, so we have the temperature dot, the rate of change of the temperature of my, my transistor is equal to, so some of you actually probably know silicon dynamics and know that this is not actually right, but it's proportional to some number times the current temperature. Okay, this is only in thermal runaway. Lithium-ion batteries also go into thermal runaway. So the FAA actually has rules on how many lithium-ion battery cells can be packed next to each other on planes that do have lots of passengers and planes that don't have lots of passengers. So they're much more okay with a big FedEx cargo plane going down with a 1 in a billion chance. But your passenger planes actually limit how many lithium-ion batteries can go in the cargo hold of your plane because there is a small, finite, kind of stochastic chance that they'll go into thermal runaway, melt a hole in the plane, and it'll go down. This does happen. Okay, so why Okay, so I have some initial temperature T naught. It has to be sufficiently high that I go into thermal runaway, so there's a break point. Now, in practice, why wouldn't my temperature just go to infinity? Right, so T at E, time T, is equal to e to the lambda time times whatever my initial temperature was. So if I let time go to infinity, this goes to infinity. I should probably draw an exponential. Okay, that's my exponential function e to the t. Why doesn't my temperature go to infinity?
External factors.
Sorry?
External factors.
External factors, okay. What do you think?
Are they going to break something, or are they going to reach equilibrium?
Okay, yeah, what's another way of saying thermal equilibrium? Right, so there's some amount of energy flux out that's balancing this. Maybe there are higher order terms as a function of temperature, like minus T cubed. Okay, so maybe I'm also radiating energy at a rate T cubed, or maybe T to the 4/3, or I forget what black body radiation is, but there's some power of T where bodies radiate out energy, right? We're all doing it right now. This remote control is radiating out energy as a function of its temperature. And so this addition of a nonlinearity allows my temperature to saturate at some very, very high value. Now, that might be above the burning point of the material, okay? Or it might not be. So my laptop right now is saturating because it's in equilibrium with how much heat it can draw out. And maybe I put a big fan on here and I multiply this by a big constant. Okay? Okay. That is my intro lecture on ODEs. These are the simplest kinds of ODEs. This is really just calculus. Okay? We have a rate of change. We manipulate our variables. We integrate them. But very, very quickly, we're going to start looking at much more complicated ODEs that model much more realistic systems. So this tiny addition of this cubic nonlinearity makes this a much harder and much more interesting problem to solve. Okay, so we're going to get into that. To do that, we're going to start by thinking a little bit more generally about these differential equations. So I'm going to take this diff EQ x dot equals lambda x. And instead of just assuming that we know a way of integrating this using calculus, or maybe I know that the derivative, right, so the derivative of e to the lambda x equals lambda e to the lambda x. Right? That's just a fact from calculus that I know. But instead of assuming those things, next time we're actually going to make another type of assumption that x can be written as a Taylor series expansion of time. Okay, so it's going to equal some constant plus another constant times time plus another constant time squared, time cubed, and so on ad infinitum. And so if you want to practice over the weekend for next week, try plugging x of t as a Taylor series expansion into this expression and solve for what these coefficients have to be. Okay, and this is really a way of deriving what e to the t kind of physically means. This is another way of deriving e to the t, or e to the lambda t. And this is going to be a very, very powerful technique we can use for nonlinear systems, higher order systems, multiple variables that are changing at once with each other. And so we're going to start looking at higher order equations like x double dot plus x equals 0. We're going to look at nonlinear equations like that, systems of equations, and we're going to start diving into that next week. Okay, so we're picking up steam. We're going to go exponential in the next few lectures until we hit some saturation, and then we're going to just keep going at a pretty high rate. Okay? Okay, that's all for today. Thanks.